Prepare to have your perception of the cosmos completely transformed. Did you know that in the vast expanse of space, there exist cosmic entities so strange, so baffling, that they challenge the very laws of physics as we understand them? We're not talking about your everyday stars and planets. We're diving headfirst into the realm of the truly bizarre. Over the next few minutes, we're embarking on a journey to uncover 25 of the most mysterious cosmic objects known to humanity, each a puzzle piece in the grand cosmic tapestry. From stars that devour their companions to entire galaxies moving in inexplicable directions, these objects defy easy explanation. Prepare to be amazed, intrigued, and perhaps a little perplexed as we explore the outer edges of the known universe. Our first stop is a cosmic predator lurking in the darkness, the Black Widow Pulsar. Cosmic Object 1, the Black Widow Pulsar is perhaps one of the most sinister objects in the cosmos. Imagine a neutron star, the ultra-dense remnant of a supernova explosion, packing more mass than our sun into a space smaller than a city. Now, picture this cosmic heavyweight relentlessly consuming its stellar neighbor. That's precisely what the Black Widow Pulsar does. This peculiar object was first identified through its intense gamma-ray emissions, a telltale sign of the energetic processes at play. It earned its chilling moniker from the spider species where the female consumes the male after mating, mirroring the pulsar's deadly feeding habits. The Black Widow Pulsar system involves a rapidly spinning neutron star, or pulsar, and a much smaller companion star locked in a tight orbit. As the pulsar spins, it emits beams of intense radiation and particles. These beams don't just harmlessly dissipate into space, they bombard the companion star, slowly vaporizing it. Over millions of years, this cosmic cannibalism leads to the gradual destruction of the companion as the pulsar feasts on its stellar neighbor. But why is the Black Widow Pulsar considered one of the deadliest objects in the universe? The answer lies in its power and proximity. The intense radiation emitted by the pulsar can be lethal to any life forms that might venture too close, and the sheer energy released during its feeding frenzies is staggering. This makes it an incredibly hostile environment, a cosmic death zone where even stars aren't safe. As we continue our cosmic journey, prepare to be equally astonished by our next stop that will bring us to one of the coldest places in the universe, the Boomerang Nebula. The second cosmic wonder on our list transports us from the fiery depths of a pulsar to the unimaginable chill of the Boomerang Nebula, the coldest known place in the universe. Can you imagine a place colder than Pluto, colder even than the background radiation of space itself? That's the Boomerang Nebula. Here, temperatures plummet to a staggering minus 272 degrees Celsius, just 1 degree above absolute zero. This cosmic icebox isn't just cold, it's also visually striking. The Boomerang Nebula gets its name from its distinctive hourglass-like shape, reminiscent of a boomerang. This unique form puzzled astronomers for years, leading to various theories about its formation. The most accepted explanation involves a star rapidly ejecting its outer layers in a powerful stellar wind. This ejection isn't uniform, it's focused into two opposing lobes, creating the nebula's characteristic shape. But what makes this stellar expulsion so cold? As the gas expands rapidly, it undergoes adiabatic cooling, similar to how air cools as it rushes out of a car tire. In the Boomerang Nebula's case, the expansion is so rapid, about 10 times faster than a typical stellar wind, that it causes an extreme drop in temperature. The Boomerang Nebula stands out as a cosmic anomaly due to its extreme temperature and rapid expansion rate. While other nebulae exhibit similar shapes, none possess the same level of coldness. This makes it a unique laboratory for studying the physics of gas dynamics and stellar evolution under extreme conditions. Now, with our perception of temperature drastically altered, let's shift gears and venture to a place of immense heat and pressure, where carbon transforms into something truly extraordinary, a diamond planet. Now, leaving behind the intense cold, we set our sights on a celestial gem, a glittering testament to the extremes of cosmic alchemy, 55 Cancri E, the diamond planet. Imagine a world twice the size of Earth, yet 8 times more massive, orbiting a sun-like star in the constellation Cancer. What sets this exoplanet apart is its composition, believed to be primarily crystalline carbon, or in simpler terms, diamond. The story of 55 Cancri E begins with its parent star, 55 Cancri, located just 40 light-years from Earth. This star hosts at least 5 planets, and 55 Cancri E is the innermost. Its proximity to its star results in a blistering surface temperature of around 1,648 degrees Celsius. Under these extreme conditions, carbon can take on a remarkable form. Scientists theorize that 55 Cancri E was once a carbon-rich star that, over billions of years, was stripped of its lighter elements. The intense heat and pressure deep within the planet then compressed the remaining carbon into a massive diamond. But how did scientists reach this sparkling conclusion? The key lies in determining the planet's density and composition. By measuring the planet's mass and radius, astronomers calculated that 55 Cancri E is incredibly dense. This, combined with the knowledge that its parent star is carbon-rich, led them to believe that the planet itself must also be primarily composed of carbon. Further calculations suggested that a significant portion of this carbon could be in the form of diamond. While we can't journey to 55 Cancri E to confirm its composition directly, its existence offers a tantalizing glimpse into the diverse possibilities of planetary formation. It challenges our assumptions about what planets can be made of and hints at the potential for other diamond worlds scattered across the cosmos. From a planet of diamond, our journey takes us to an enigma of gravitational pull. Next, we'll explore a place where galaxies themselves are drawn toward a mysterious, unseen force, the Great Attractor. Switching gears, let's journey to a place far beyond our local galaxies, a region of space shrouded in mystery and immense gravitational power, the Great Attractor. This cosmic anomaly is not a single object, but rather a region in space that exerts a gravitational pull so strong that it affects the motion of galaxies, including our own Milky Way, over hundreds of millions of light-years. The Great Attractor lies in the direction of the constellations Centaurus and Hydra, but it's hidden behind a region of space known as the Zone of Avoidance. This zone is obscured by the dust and gas of our own galaxy, making it incredibly difficult to directly observe the Great Attractor and understand its true nature. Imagine trying to spot a faint light through a thick fog. That's the challenge astronomers face when studying this region. Despite these challenges, scientists have been able to map the movement of galaxies in the area, revealing a clear flow of cosmic objects toward a central point. This gravitational pull is so significant that it influences the motion of the local group, the collection of galaxies that includes the Milky Way and Andromeda. So, what could be responsible for such a powerful gravitational force? Some theories suggest that the Great Attractor is a supercluster of galaxies, an immense collection of thousands of galaxies bound together by gravity. However, the visible mass of these galaxies doesn't seem sufficient to account for the observed gravitational effects. This has led to speculation that a significant amount of dark matter, the mysterious substance that makes up a large portion of the universe's mass, may be concentrated in this region. Perhaps the Great Attractor is a massive yet unseen concentration of dark matter that amplifies the gravitational pull beyond what we can observe with telescopes. Studying the Great Attractor is crucial to understanding the large-scale structure of the universe and the role of gravity in shaping the cosmos. It helps us piece together the complex web of galaxies and the forces that govern their movement. Unveiling the secrets of this gravitational anomaly could provide valuable insights into the distribution of dark matter and the fundamental laws of physics that govern the universe. As research continues, scientists are employing advanced techniques, such as mapping the velocities of distant galaxies and using gravitational lensing to probe the distribution of mass in the region. These efforts may eventually reveal the true nature of the Great Attractor and its place in the cosmic tapestry. From an invisible gravitational force shaping the movements of galaxies, we turn our attention to a cosmic cannibal, a galaxy that grows by consuming its neighbors, and that brings us to our next point. Now prepare to witness a spectacle of galactic proportions as we turn our gaze towards the cannibal galaxy. Known as NGC 1316, this cosmic behemoth doesn't just peacefully coexist with its neighbors, it devours them. Imagine a cosmic Pac-Man slowly but surely consuming everything in its path. Located approximately 60 million light-years away in the constellation Fornax, NGC 1316 is a lenticular galaxy, a sort of hybrid between a spiral and an elliptical galaxy. But what truly sets it apart is its insatiable appetite for smaller galaxies. This galactic cannibalism isn't a quick, violent event, but rather a slow, methodical process that unfolds over billions of years. As smaller galaxies venture too close to NGC 1316, they become ensnared by its immense gravitational pull. Tidal forces, the same forces that cause tides on Earth, begin to distort and stretch the smaller galaxy, gradually tearing it apart. The stars and gas from the unfortunate galaxy are then slowly incorporated into NGC 1316, adding to its size and mass. The evidence of this cosmic feast is visible in NGC 1316's peculiar structure. It exhibits faint shells and loops of stars, remnants of galaxies it has consumed in the past. These delicate structures are like ghostly echoes of galactic meals long gone. Studying NGC 1316 provides valuable insights into how galaxies evolve and grow over cosmic time. Galactic cannibalism is thought to be a common process in the universe, particularly in dense environments like galaxy clusters. By observing galaxies like NGC 1316 in action, astronomers can learn about the dynamics of galactic interactions and the role they play in shaping the universe. Moreover, the cannibalistic behavior of NGC 1316 may also trigger bursts of star formation within the galaxy. As gas from the consumed galaxies falls into the central region, it can collide and compress, leading to the birth of new stars. This can give the cannibal galaxy a temporary burst of youthful energy, contrasting with its otherwise old and settled stellar population. From a galaxy with a taste for destruction, we now go to a nebula with a unique shape. Next, we will explore the geometric oddity of the Red Rectangle Nebula. Cosmic Object 6, the Red Rectangle Nebula, is a sight that truly defies expectations. Imagine a celestial object that looks less like a cloud of gas and dust and more like a meticulously crafted piece of cosmic origami. This nebula, officially known as HD 44179, stands out due to its remarkably geometric shape, resembling a perfect rectangle in many observations. The Red Rectangle Nebula is located approximately 2,300 light-years away in the constellation Monoceros. Its most striking feature is its ladder-like structure, with clearly defined edges and rungs that create a visually stunning spectacle. This geometric precision is highly unusual for nebulae, which typically exhibit more amorphous and irregular shapes. The formation of the Red Rectangle Nebula is intimately linked to the presence of a binary star system at its center. These two stars, locked in a close orbit around each other, play a crucial role in shaping the nebula's unique structure. One of the stars is a red giant nearing the end of its life, shedding its outer layers into space. As the ejected material expands outward, it interacts with the gravitational forces and magnetic fields of the binary system, leading to the formation of the distinct rectangular shape. The precise mechanisms through which the binary stars sculpt the nebula are still not fully understood, but it's believed that the interaction between the stars and the ejected material creates a series of dense rings or disks. These structures then act as masks, blocking the light from the central stars and casting shadows that define the edges of the rectangle. Another key factor contributing to the red rectangle's odd shape is the presence of polycyclic aromatic hydrocarbons, or PAH, within the nebula. These complex organic molecules, which are also found on Earth, absorb ultraviolet light from the central stars and re-emit it at longer wavelengths, giving the nebula its characteristic red hue. The PAHs may also play a role in the formation of the nebula's structure by influencing the way the gas and dust interact with light and magnetic fields. What makes the Red Rectangle Nebula a cosmic oddity is not just its shape but also its evolutionary stage. It represents a brief transitional phase in the life cycle of a star as it transforms from a red giant into a planetary nebula. The Red Rectangle is essentially a pre-planetary nebula, a snapshot of a star system on the cusp of a dramatic transformation. This makes it a valuable object for astronomers studying the late stages of stellar evolution. From a nebula with a strange shape shifting to a star that defies death, up next we explore the secrets of the zombie star and see what makes it so unique. The seventh cosmic object deals with a fascinating concept that blurs the lines between stellar life and death, the zombie star. These aren't the undead from a horror movie, but rather a real astronomical phenomenon involving a specific type of supernova known as Type 1X. Unlike typical Type 1, a supernova, which result in the complete destruction of a white dwarf star, Type 1X supernova leave behind a remnant, a so-called zombie star that has survived its own explosion. The standard model of a Type 1 supernova involves a white dwarf star accreting matter from a companion star, typically a red giant. As the white dwarf gains mass, it eventually reaches the Chandrasekhar limit, which is approximately 1.4 times the mass of our Sun. At this point, the core of the white dwarf becomes unstable, triggering a runaway nuclear fusion reaction that obliterates the entire star in a brilliant explosion. However, in a Type 1X supernova, the explosion is weaker and less energetic. Instead of completely disintegrating, a portion of the white dwarf survives, albeit significantly altered. This surviving remnant is what astronomers refer to as a zombie star. One of the leading theories explaining these undead stars involves a process called deflagration, where the nuclear fusion reaction propagates subsonically through the white dwarf. This slower burning process doesn't generate enough energy to completely unbind the star, leaving behind a bound remnant. Another possibility is that the companion star plays a more active role in disrupting the explosion, siphoning off energy and mass before the white dwarf can be completely destroyed. The discovery of zombie stars has profound implications for our understanding of stellar life cycles and the diversity of supernova. It challenges the long-held assumption that all Type 1 supernova result in complete stellar destruction, revealing a more nuanced picture of stellar evolution. These surviving stars provide a unique opportunity to study the conditions and processes that occur during a supernova explosion in real time. By analyzing the composition and behavior of zombie stars, astronomers can gain insights into the nature of nuclear fusion, the dynamics of stellar explosions, and the ultimate fate of stars. The study of zombie stars is still in its early stages, and many questions remain unanswered. However, one thing is clear: these stellar survivors are rewriting the textbooks and pushing the boundaries of our knowledge about the universe. As we continue our journey through the cosmos, prepare to be amazed by our next stop, a star with erratic dimming patterns that sparked theories of alien megastructures, the enigmatic Tabby star. As we continue our cosmic exploration, let's delve into the mystery of another strange celestial object, Tabby star, officially known as KIC 8462852. This star, located about 1,480 light-years away in the constellation Cygnus, gained notoriety for its unusual and erratic dimming patterns. Unlike typical stars that exhibit minor brightness variations due to orbiting planets, Tabby's star experiences significant and irregular dips in luminosity, sometimes as much as 22%. These dramatic dimming events sparked widespread speculation and captured the public's imagination, leading to one particularly intriguing, albeit unlikely, hypothesis: alien megastructures. The idea, initially proposed by some astronomers, suggested that an advanced extraterrestrial civilization might have constructed massive structures, such as Dyson spheres, around the star to harness its energy. These structures, as they pass between the star and our telescopes, could explain the observed dimming patterns. While the alien megastructure theory captured the zeitgeist, scientists have also explored more conventional, natural explanations for Tabby's star's peculiar behavior. One leading hypothesis involves a swarm of comets orbiting the star. According to this model, a large group of comets, perhaps resulting from the breakup of a larger object, could be passing in front of the star, causing the observed dips in brightness. Another explanation suggests the presence of circumstellar dust and debris. This dust could be unevenly distributed around the star, leading to variable obscuration as it orbits. Although these natural explanations seem more plausible, they don't fully account for all the observed characteristics of Tabby's star. The irregular timing and magnitude of the dimming events remain challenging to explain with current models. Despite extensive research and observation, Tabby's star continues to be an enigma. Scientists are still actively studying its behavior, collecting more data, and refining their theories. The star serves as a reminder of the vastness and complexity of the universe, as well as the limits of our current understanding. While the possibility of alien megastructures remains a tantalizing thought, the leading scientific explanations highlight the importance of critical thinking and the ongoing quest to unravel the mysteries of the cosmos. Up next, we'll journey to a galaxy that's not just unusual but downright bizarre, the rare ring galaxy known as Hoag's Object. The ninth cosmic object on our list brings us to a truly unique sight, the Hoag's Object. This galaxy stands out due to its nearly perfect ring shape, making it a rare and visually stunning cosmic entity. Located approximately 600 million light-years away, Hoag's Object captivates astronomers with its distinct structure, a bright, circular ring composed of young, blue stars surrounding a central core of much older, reddish stars. The gap between the outer ring and the central body appears almost completely empty, adding to the galaxy's mystique. The formation of Hoag's Object remains a subject of scientific debate. One leading theory suggests that it may have resulted from a polar ring galaxy merging with another galaxy nearly head-on. This collision could have stripped away most of the intervening matter, leaving behind a separated core and ring. Another hypothesis proposes that Hoag's Object was once a spiral galaxy that underwent a unique type of instability. This instability could have caused the spiral arms to detach and form the ring structure we observe today. What sets Hoag's Object apart from other galaxies is its distinct morphology. Most galaxies fall into well-defined categories such as spiral, elliptical, or irregular. Ring galaxies themselves are rare, but Hoag's Object is particularly unusual because of its well-defined circular ring and relatively empty space between the ring and the central core. This clear separation is not commonly seen in other ring galaxies, making Hoag's Object a valuable case study for understanding galaxy formation and evolution. The extreme regularity and clarity of its ring structure make Hoag's Object especially puzzling. While collisions or internal dynamics can produce ring galaxies, achieving such a perfect and stable configuration is not easy. The object challenges existing models of galaxy formation and prompts ongoing research to refine our understanding of the processes that shape these cosmic structures. The mystery surrounding Hoag's Object serves as a testament to the diversity and complexity of the universe, reminding us that there are still many cosmic wonders waiting to be fully understood. Transitioning from this peculiar ring galaxy, we now turn our attention to a phenomenon that challenges our understanding of cosmic motion, the mysterious dark flow. Cosmic Object 10, the dark flow. Venturing further into the enigmas of space, we encounter a phenomenon that seems to defy our conventional understanding of the cosmos, the dark flow. This term describes an unusual movement of galaxy clusters in a specific direction, seemingly unaffected by the expansion of the universe. Observations have revealed that numerous galaxy clusters are moving towards a particular region in space, at speeds that cannot be accounted for by known gravitational forces alone. This collective motion challenges the cosmological principle, which assumes that the universe on a large scale is uniform and isotropic, meaning it looks the same in all directions. The existence of the dark flow was initially detected through observations of the cosmic microwave background, or CMB. Scientists noticed subtle temperature variations in the CMB caused by the movement of galaxy clusters. These variations, known as the Sunyaev-Zeldovich effect, indicated that clusters were moving in a coordinated manner. The surprising aspect was that this motion persisted even at great distances, suggesting a force beyond the currently observable universe was at play. Several theories have been proposed to explain the dark flow. One of the most intriguing suggests that the gravitational influence of structures beyond the visible universe might be responsible. These structures residing outside our cosmic horizon could be exerting a pull on our observable universe, causing the galaxy clusters to drift in their direction. Another theory considers the possibility of pre-inflationary remnants, relics from the universe's earliest moments, influencing the motion of matter today. These remnants could have created density variations that affect the gravitational landscape on a grand scale. The concept of the dark flow opens up profound possibilities, including the potential existence of other universes. If the gravitational pull is indeed originating from beyond our observable universe, it might indicate the presence of other universes interacting with ours. These interactions could be subtle, yet significant enough to leave their imprint on the motion of galaxy clusters. While such ideas remain speculative, they highlight the far-reaching implications of the dark flow and its potential to revolutionize our understanding of the cosmos. As we continue to study this mysterious phenomenon, we may uncover new insights into the fundamental nature of the universe and its connection to realms beyond our current perception. From the mysterious drift of the dark flow, our journey now takes us to a star that has stood the test of time, challenging our very understanding of the age of the universe, the Methuselah star. Cosmic Object 11, the Methuselah star. Now, shifting our gaze from the enigmatic movements of galaxies to the individual stars, we arrive at a celestial body that has astronomers scratching their heads, HD 140283, also known as the Methuselah star. This ancient star, located approximately 190 light-years from Earth in the constellation Libra, is one of the oldest known stars in the universe. Its estimated age presents a significant challenge to our understanding of cosmology, particularly the timeline of the Big Bang. The Methuselah star is a subgiant star, meaning it is in a late stage of its life, having exhausted the hydrogen fuel in its core and beginning to expand. What makes it particularly intriguing is its estimated age, which, according to initial calculations, appeared to be older than the universe itself. While subsequent measurements and revisions have brought the star's age more in line with cosmological models, it still hovers around 14.46 plus or minus 0.8 billion years. Given that the accepted age of the universe is approximately 13.8 billion years, the Methuselah star remains a cosmic anomaly. The challenge arises from the methods used to determine the age of stars. These methods rely on factors such as a star's composition, temperature, and distance. By analyzing the Methuselah star's low metal content, which indicates it formed very early in the universe's history, scientists can estimate its age. However, uncertainties in these measurements, particularly regarding the star's precise distance and composition, contribute to the age discrepancy. The star's age was refined using data from the Hubble Space Telescope, which helped to more accurately determine its distance and movement. Despite these refinements, the Methuselah star continues to intrigue scientists. Its existence implies that either our measurements of the universe's age are slightly off, or our understanding of stellar evolution requires further adjustments. The Methuselah star serves as a reminder of the complexities and uncertainties in unraveling the universe's history, prompting ongoing research and debate. As we delve deeper into the cosmos, prepare to be amazed by stars ejected from galaxies at incredible speeds, known as hypervelocity stars. Cosmic Object 12, the hypervelocity stars. Imagine stars not gently orbiting within the confines of a galaxy, but rather stars ejected from their galactic home at mind-bending speeds. These are hypervelocity stars, stellar projectiles hurtling through the intergalactic void at hundreds of kilometers per second. Their existence was first theorized in the 1980s, but it wasn't until 2005 that the first such star was confirmed, forever changing our understanding of galactic dynamics. The origins of these cosmic bullets are often traced back to supermassive black holes lurking at the centers of galaxies. In a scenario known as the Hill's mechanism, a binary star system ventures too close to the black hole. The immense gravitational forces tear the binary apart, capturing one star into orbit around the black hole while flinging the other outward at tremendous velocity. This ejected star becomes a hypervelocity star, embarking on a lonely journey through the cosmos. But how do these stars achieve such incredible speeds? The gravitational slingshot effect imparted by the supermassive black hole is the key. As the binary star system interacts with the black hole's intense gravity, energy is transferred to one of the stars, accelerating it to speeds that can exceed the galaxy's escape velocity. These stars can travel millions of light years before eventually succumbing to the gravitational pull of another galaxy, or simply fading away into the darkness. The impact of hypervelocity stars on the cosmos is multifaceted. Their existence provides valuable insights into the distribution of dark matter in and around galaxies. By studying their trajectories, scientists can map out the gravitational landscape and probe the mysteries of dark matter's influence. Furthermore, hypervelocity stars contribute to the intergalactic medium, enriching it with stellar material and influencing the chemical evolution of the universe. As we continue our cosmic journey, our next destination is a look into the El Gordo galaxy cluster and explore its role in understanding dark matter. Transitioning from individual rogue stars to colossal cosmic structures, our next stop is the El Gordo galaxy cluster, a behemoth whose very existence challenges our understanding of the universe. Officially known as ACDCL 0102-4915, El Gordo, Spanish for the Fat One, is one of the largest and most massive galaxy clusters ever discovered. Its discovery in 2011 sent ripples through the astrophysics community, offering a unique window into the interplay of dark matter, gravity, and cosmic evolution. The sheer size of El Gordo is staggering. It's not just a collection of galaxies, it's a collision of two massive galaxy clusters merging at tremendous speeds. This merger has created a cosmic maelstrom of hot gas, superheated plasma, and dark matter, all swirling together in a region millions of light years across. Within this chaotic environment, thousands of galaxies jostle for position, their movements dictated by the immense gravitational forces at play. But what makes El Gordo particularly intriguing is its role in unraveling the mysteries of dark matter. Scientists estimate that the majority of El Gordo's mass is composed of dark matter, an invisible substance that doesn't interact with light but exerts a powerful gravitational pull. By studying the distribution of galaxies and hot gas within El Gordo, researchers can infer the underlying distribution of dark matter and test our models of cosmic structure formation. The El Gordo galaxy cluster continues to be a focal point for scientific investigations as we move on to explore a world of nearly massless particles with ghostly neutrino that pass through everything. Now, shifting our focus from clusters of galaxies to the infinitesimally small, we encounter the ghostly neutrino, a subatomic particle renowned for its elusive nature. Often dubbed ghost particles, neutrinos are nearly massless and electrically neutral, allowing them to pass through virtually anything without interaction. Billions of neutrinos stream through our bodies every second, originating from the Sun, distant stars, and even the Earth itself. Neutrinos play a crucial role in some of the most dramatic events in the universe, particularly supernova. During a supernova, a massive star collapses under its own gravity, triggering a cataclysmic explosion. In the heart of this explosion, neutrinos are produced in staggering numbers. These neutrinos carry away a significant portion of the energy released during the collapse, contributing to the outward shockwave that rips the star apart. Detecting these neutrinos provides valuable insights into the inner workings of supernova, allowing scientists to probe conditions that are otherwise inaccessible. Despite their abundance, neutrinos are notoriously difficult to detect due to their weak interactions with matter. Scientists use massive underground detectors like the Super Kamiok and in Japan or the Ice Cube Neutrino Observatory in Antarctica to catch these elusive particles. These detectors rely on rare instances where a neutrino interacts with an atomic nucleus, producing a tiny flash of light that can be detected by sensitive instruments. By studying these interactions, scientists can learn about the properties of neutrinos, such as their mass and their behavior. The study of neutrinos has opened new windows into the fundamental laws of physics and the extreme environments of the cosmos, as we turn our attention to the mystery of stars appearing younger than their age with the blue stragglers. Cosmic Object 15. The blue stragglers describe stars that appear younger than their surroundings, discuss their formation, how they defy stellar aging, and their significance in star clusters. Amidst the vast cosmic tapestry, some stars seem to defy the conventional aging process. These stellar anomalies, known as blue stragglers, appear younger and bluer than their neighbors within star clusters. In a typical star cluster, stars form at roughly the same time and age together, with more massive stars evolving and burning out faster than their smaller counterparts. However, blue stragglers buck this trend, maintaining a youthful appearance that perplexes astronomers. One of the primary mechanisms behind the formation of blue stragglers is thought to be stellar mergers. In dense star clusters, stars can collide and merge, creating a new, more massive star. This merged star inherits the combined mass of its progenitors, effectively resetting its aging clock. Since a more massive star is typically hotter and bluer, the resulting merger product appears younger than the surrounding stars that have already begun to age and cool down. Another proposed mechanism involves mass transfer in binary star systems. In these systems, one star can siphon off material from its companion, increasing its own mass and rejuvenating its appearance. This process allows the mass-gaining star to extend its lifespan and maintain its blue hue, standing out against the backdrop of older, redder stars. The existence of blue stragglers provides valuable insights into the dynamics and evolution of star clusters. Their presence suggests that stellar interactions, such as mergers and mass transfer, play a significant role in shaping the demographics of these clusters. By studying the properties of blue stragglers, astronomers can learn about the frequency of stellar collisions, the prevalence of binary star systems, and the overall age and history of the clusters in which they reside. These enigmatic stars challenge our understanding of stellar evolution, reminding us that the cosmos is full of surprises, but the cosmos is also full of surprises powered by quasars. So let's explore the most energetic outflows in the universe in our next section. Cosmic Object 16, the quasar tsunami, explore the most energetic outflows in the universe powered by quasars. Explain how these outflows shape galaxies and their role in cosmic evolution. Emerging from the hearts of galaxies, quasars unleash some of the most energetic outflows in the universe, often referred to as quasar tsunamis. These outflows, driven by the immense power of supermassive black holes, play a crucial role in shaping the evolution of galaxies. Quasars are incredibly luminous objects powered by supermassive black holes at the centers of galaxies. As matter falls towards these black holes, it forms an accretion disk which heats up to extreme temperatures and emits vast amounts of radiation across the electromagnetic spectrum. This process generates powerful outflows of gas and particles that can extend far beyond the quasar itself, impacting the surrounding galaxy. The outflows from quasars can take several forms, including fast-moving winds and collimated jets. These outflows carry tremendous amounts of energy and momentum, capable of influencing the gas content, star formation rate, and overall structure of the host galaxy. One of the primary ways quasar outflows shape galaxies is by regulating star formation. As the outflows sweep through the galaxy, they can compress and heat the surrounding gas, either triggering or suppressing the formation of new stars. In some cases, the outflows can expel large quantities of gas from the galaxy, effectively starving it of the material needed to form stars. This process, known as feedback, can play a crucial role in limiting the growth of galaxies and preventing them from becoming overly massive. Furthermore, quasar outflows can also influence the distribution of elements within galaxies. The outflows can transport heavy elements synthesized in the cores of stars from the central regions of the galaxy to its outskirts. This process enriches the interstellar medium with metals, which can then be incorporated into future generations of stars. By studying the properties of quasar outflows, astronomers can gain valuable insights into the complex interplay between supermassive black holes and their host galaxies. These outflows provide a mechanism for energy and matter to be transferred from the central black hole to the rest of the galaxy, influencing its evolution over cosmic time. The impact of these quasar tsunamis on the universe leads us to our next exploration, the realm of ultramagnetic neutron stars. Transitioning from the immense scale of quasar tsunamis, we now turn our attention to another cosmic phenomenon defined by its extreme properties, magnetars. Magnetars are a type of neutron star characterized by their incredibly powerful magnetic fields, far stronger than anything found on Earth. These cosmic objects generate magnetic fields that can be 1,000 times stronger than those of typical neutron stars and trillions of times stronger than Earth's magnetic field. This extreme magnetism leads to a variety of unique and often violent phenomena. Magnetars are typically formed in supernova explosions when massive stars collapse at the end of their lives. Under the right conditions, the collapsing core of the star can spin rapidly and possess a strong magnetic field. This combination amplifies the magnetic field to the extreme levels observed in magnetars. The exact mechanisms behind magnetar formation are still not fully understood, and they are an active area of research in astrophysics. The magnetic fields of magnetars are so intense that they can have devastating effects on their surroundings. These effects are capable of ripping apart atoms and creating powerful bursts of electromagnetic radiation. Magnetars are known to emit intense bursts of X-rays and gamma rays, some of which can be detected across vast distances. These bursts can last from fractions of a second to several minutes and are among the brightest events in the universe. The immense energy released during these bursts poses a significant threat to any nearby objects or life forms. Even at distances of many light years, a magnetar flare could disrupt planetary atmospheres and cause widespread damage. Due to their extreme nature, magnetars provide valuable insights into the physics of matter under extreme conditions. Studying these objects helps scientists understand more about neutron stars, magnetic fields, and the fundamental laws of nature. As we continue our cosmic journey, our next stop brings us to perhaps one of the most visually stunning wonders of the universe and a testament to ongoing creation. Transitioning now from the forces of destruction to monuments of creation, we turn our gaze towards the pillars of creation. These iconic structures reside within the Eagle Nebula, a star-forming region about 70,000 light-years from Earth in the constellation Serpens. The pillars of creation are composed of interstellar gas and dust, sculpted by the powerful radiation and stellar winds from nearby hot, young stars. These pillars are not only visually stunning but also play a crucial role in the ongoing birth of new stars. The formation of the pillars of creation is a dynamic process, shaped by the intense energy emitted by the cluster of massive stars known as NGC 1681, located near the nebula. The ultraviolet radiation from these stars erodes the surrounding gas and dust clouds, carving out the distinctive pillar-like structures we observe. Denser regions within the clouds are more resistant to this erosion, creating the pillars as the less dense material is gradually blown away. This process, known as photo-erosion, sculpts the pillars into their intricate shapes, revealing the ongoing interplay between creation and destruction within the nebula. Within the pillars of creation, new stars are being born. The dense pockets of gas and dust within the pillars collapse under their own gravity, forming protostars. These protostars gather more material from their surroundings, eventually igniting nuclear fusion in their cores and becoming fully fledged stars. The pillars of creation thus serve as stellar nurseries, nurturing the birth of new stars within their protective embrace. The process of star formation within these pillars contributes to the ongoing evolution of the Eagle Nebula and the broader galaxy. However, the very stars that sculpt and illuminate the pillars of creation will also eventually lead to their demise. The intense radiation and stellar winds from the massive stars will continue to erode the pillars, gradually dispersing the gas and dust. Eventually, the pillars will be completely eroded, and their material will be incorporated into the surrounding interstellar medium, ready to form new structures and stars in the distant future. What awaits then is a look at other phenomena like the Fermi bubbles that challenge how we imagine galaxies. Shifting our perspective from stellar nurseries to galactic phenomena, we now turn to the Fermi bubbles. These are immense, mysterious structures emitting gamma rays, towering above and below the Milky Way's galactic plane. Their discovery in 2010 by the Fermi Gamma Ray Space Telescope has presented a fascinating puzzle to astronomers, sparking numerous theories about their origin and impact on our galaxy. The Fermi bubbles extend approximately 25,000 light-years above and below the galactic center, making them some of the largest structures in our galaxy. They are characterized by their high-energy gamma-ray emission, as well as the presence of energetic particles and magnetic fields. The bubbles appear to have relatively sharp edges, suggesting they were formed by a sudden and powerful event. The exact nature of these structures is still a topic of active research, but scientists are exploring several compelling hypotheses about their origin. One prominent theory suggests that the Fermi bubbles are the result of past activity from the supermassive black hole at the center of the Milky Way, known as Sagittarius A star. According to this scenario, Sagittarius A star may have experienced periods of intense accretion, during which it consumed large amounts of gas and dust. This process could have generated powerful jets of energy and particles that inflated the bubbles, creating the structures we observe today. Alternatively, the bubbles may have been formed by a burst of star formation in the galactic center, with the combined energy from numerous supernovae driving the expansion of the bubbles. Regardless of their precise origin, the Fermi bubbles have had a significant impact on the Milky Way. The energy and particles released by the bubbles have likely influenced the distribution of gas and magnetic fields in the galactic halo. They may also have played a role in regulating the rate of star formation in the galaxy by injecting heat and turbulence into the surrounding interstellar medium. Ongoing research into the Fermi bubbles promises to shed light on the complex interplay between supermassive black holes, star formation, and the evolution of galaxies. Considering the Milky Way's features, attention is turned to the peculiar interstellar object Oumuamua. Transitioning from gamma-ray emitting bubbles to a visitor from beyond, consider Oumuamua, the interstellar object that zipped through our solar system. This space rock, detected in 2017, sparked intense curiosity and debate due to its unusual characteristics and behavior. Oumuamua, meaning scout in Hawaiian, was the first confirmed object from another star system to be observed passing through our own. Its elongated shape, reddish color, and peculiar acceleration as it moved away from the Sun made it unlike anything astronomers had seen before. One of Oumuamua's most striking features was its highly elongated shape, often described as cigar-like or pancake-like. Estimates suggest it could be as long as 400 meters, but only a few tens of meters wide. This extreme aspect ratio is unlike that of any asteroid or comet observed in our solar system. Furthermore, Oumuamua's reddish hue indicates that it has been exposed to cosmic radiation for millions or even billions of years, suggesting it has traveled through interstellar space for an extremely long time. Adding to the mystery, Oumuamua exhibited a non-gravitational acceleration as it moved away from the Sun. This means that it sped up more than could be explained by the Sun's gravity alone. While comets often exhibit such behavior due to the outgassing of volatile materials, no coma or tail was observed around Oumuamua. This led to speculation about the nature of the forces acting on it, with some scientists suggesting the possibility of a thin, lightweight structure acting like a solar sail. The true origin and composition of Oumuamua remain a topic of ongoing debate. While some researchers believe it is a natural object, possibly a fragment of a planet or a comet ejected from its home star system, others have entertained more exotic explanations, including the possibility that it could be an alien artifact. As Oumuamua fades into the distance, astronomers are actively searching for other interstellar visitors, hoping to unlock more secrets of the cosmos. Now let's shift our focus to the hypothetical realm of dark stars. Turning our gaze toward theoretical possibilities, let's consider the intriguing concept of dark stars, hypothetical celestial objects powered by dark matter. Unlike conventional stars that generate energy through nuclear fusion, dark stars are theorized to be sustained by the annihilation of dark matter particles within their cores. This concept arises from the nature of dark matter, which, while making up a significant portion of the universe's mass, interacts very weakly with ordinary matter. The theoretical existence of dark stars hinges on the idea that dark matter particles can collide and annihilate each other, releasing energy in the process. In the early universe, when the density of dark matter was much higher, these annihilations could have generated enough heat to prevent gas clouds from collapsing and forming regular stars. Instead, these clouds could have formed dark stars, which would be much larger and more diffuse than their nuclear-burning counterparts. One of the primary differences between dark stars and regular stars lies in their energy source and composition. Regular stars are composed primarily of hydrogen and helium and produce energy through nuclear fusion. Dark stars, on the other hand, would be composed primarily of hydrogen and helium as well, but with a significant amount of dark matter concentrated in their cores. The energy produced by dark matter annihilation would heat the star, causing it to glow, but at a much lower temperature than a regular star. This means that dark stars would emit light at different wavelengths, making them potentially detectable through infrared or microwave telescopes. The potential role of dark stars in the early universe is significant. If they existed, they could have influenced the formation of the first galaxies and the distribution of matter in the cosmos. Their presence could also explain some of the observed properties of early galaxies, such as their high luminosity and unusual chemical composition. Although dark stars remain hypothetical, ongoing research into dark matter, and the early universe may one day confirm their existence, shedding new light on the mysteries of the cosmos. As we ponder the possibility of dark matter-fueled stars, we now turn our attention to one of the largest known structures in the universe. Transitioning from the realm of hypothetical stars, now let's turn our attention to a real, mind-boggling structure that dwarfs even galaxies, the Hercules Corona Borealis Great Wall. This immense cosmic filament is one of the largest known structures in the observable universe, challenging our understanding of how such vast formations could arise within the current cosmological models. Its discovery stemmed from mapping the locations of gamma-ray bursts across the sky. By analyzing the distribution of these bursts, astronomers noticed an unusually high concentration in a specific region, revealing the presence of this colossal structure. The size of the Hercules Corona Borealis Great Wall is truly staggering. It spans approximately 10 billion light-years in length, making it far larger than the typical superclusters of galaxies. To put that in perspective, it would take light 10 billion years to travel from one end of the structure to the other. This immense scale presents a significant challenge to our understanding of the universe because the standard cosmological model suggests that structures of this size should not exist. According to the model, the universe is homogeneous on large scales, meaning that matter should be evenly distributed. However, the existence of the Hercules Corona Borealis Great Wall demonstrates that matter can, in fact, clump together to form incredibly large structures, defying the expected uniformity. The challenges that the Hercules Corona Borealis Great Wall poses to cosmology are multifaceted. It questions the validity of the cosmological principle, which assumes that the universe looks roughly the same no matter where you are observing it from. The existence of such a large structure suggests that there might be regions of the universe that are significantly different from others. Furthermore, the formation of the Great Wall within the time frame allowed by the age of the universe is difficult to explain. It challenges our understanding of how gravity and other forces could have acted to assemble such a massive structure in such a relatively short period. As scientists continue to study this colossal structure, the puzzles are many, and what could be the role of ringed exoplanets in this Great Wall? Transitioning from the challenges of understanding the Hercules Corona Borealis Great Wall, let's now venture into the realm of theoretical astrophysics and explore a bizarre, hypothetical object known as the Thorne-Zitkow object. This fascinating celestial body, often abbreviated as TZO, represents a unique type of hybrid star with a neutron star residing at its very core. The concept was first proposed by Kip Thorne and Anna Zitkow in 1977, and since then it has intrigued astronomers and physicists alike. A Thorne-Zitkow object is theorized to form when a neutron star collides with and merges into a red giant or supergiant star. This collision is a rare event in itself, requiring a specific set of circumstances. For example, in a binary star system, if one star evolves into a neutron star and the other expands into a red giant, the neutron star could spiral into the core of the red giant, initiating the formation of a TZO. What sets a Thorne-Zitkow object apart from regular stars is its unusual internal structure and the exotic nuclear reactions that occur within. Unlike ordinary stars where nuclear fusion takes place in the core, a TZO has a neutron star at its center, surrounded by layers of stellar material from the red giant. The neutron star's intense gravity compresses the surrounding material, leading to extreme densities and temperatures. This environment facilitates unique nuclear reactions that are not typically observed in normal stars. These reactions result in the production of unusual elements and isotopes, offering a distinct chemical signature that could potentially be used to identify TZOs. Detecting these objects observationally is quite challenging, given their rarity and the difficulty in distinguishing them from regular red giants or supergiants. However, scientists have proposed that the presence of certain elements, such as an excess of rubidium, strontium, yttrium, zirconium, or molybdenum, could serve as telltale signs of a Thorn-Zitkau object. The rarity of Thorn-Zitkau objects stems from the specific conditions required for their formation. Not only does there need to be a collision between a neutron star and a red giant, but the collision must also occur in a way that allows the neutron star to sink into the core without completely disrupting the star. Moreover, the resulting TZO is believed to have a relatively short lifespan on astronomical timescales. The intense nuclear reactions and energy output cause the star to evolve rapidly, eventually leading to its destruction or transformation into a different type of object. Despite their hypothetical nature, Thorn-Zitkau objects offer valuable insights into stellar evolution, nuclear physics, and the extreme environments that can exist in the universe. Although, let's shift our perspective to another strange cosmic object. We'll explore a planet with rings far grander than those of Saturn, a cosmic oddity known as the ringed exoplanet J1407b. Cosmic Object 24. The ringed exoplanet. Imagine a planet whose ring system dwarfs that of Saturn, extending hundreds of millions of kilometers into space. Such is the spectacle of J1407b. This ringed exoplanet, orbiting a young sun-like star approximately 434 light-years away in the constellation Centaurus, presents one of the most extraordinary sights in our known universe. Its discovery in 2012 by a team led by Rochester University astronomer Eric Mumajek marked a significant milestone in exoplanetary science. The scale of J1407b's ring system is truly staggering. It is 200 times larger than Saturn's rings, containing over 37 distinct rings, with each ring spanning tens of millions of kilometers. If Saturn were to be replaced by J1407b in our solar system, its rings would dominate the night sky, appearing much larger than the full moon. The immense size and complexity of its ring system have captured the imagination of astronomers and space enthusiasts alike. The discovery of J1407b was made through the analysis of data from the SuperWASP project, a wide-angle search for planets that transit or pass in front of their host stars. When J1407b transited its star, J1407, the light from the star dimmed in a highly unusual pattern. This transit lasted for 56 days, indicating that the object blocking the star's light was significantly larger and more complex than a typical planet. Detailed modeling of the light curve revealed the presence of numerous rings, each with varying densities and widths. Some of these rings were found to contain gaps similar to those observed in Saturn's rings, potentially caused by orbiting moons or other gravitational disturbances. These gaps and the overall structure of the ring system suggest that J1407b may be in the process of forming moons. The rings of J1407b are thought to consist of dust particles, icy debris, and potentially even nascent moons. The total mass of the ring system is estimated to be several times that of Earth. The presence of such a massive ring system around a planet is rare and provides valuable insights into the formation and evolution of planetary systems. J1407b challenges our understanding of how planets and moons form, suggesting that ring systems can play a more significant role in the process than previously thought. The existence of J1407b also suggests that ringed exoplanets might be more common than we previously assumed, and future surveys could reveal even more such objects, further expanding our knowledge of the diversity of planetary systems. Let's shift our focus to another captivating cosmic entity, the cosmic web, the large-scale structure of the universe. Cosmic Object 25. The cosmic web. Envision a colossal, sprawling network that spans billions of light-years, a structure so immense that galaxies themselves appear as mere nodes within its intricate design. This is the cosmic web. Also known as the large-scale structure of the universe, it is composed primarily of dark matter, along with filaments of gas, connecting galaxies and galaxy clusters in a vast, interconnected web. Its role in the universe's structure is fundamental, serving as the scaffolding upon which all visible matter is organized. The cosmic web influences the distribution of galaxies, directs the flow of matter, and shapes the evolution of cosmic structures. This web-like structure arises from the gravitational amplification of tiny density fluctuations in the early universe. Over billions of years, gravity has pulled matter together, forming dense regions where galaxies cluster and vast voids where matter is scarce. These dense regions and voids are connected by filaments of dark matter and gas, creating a web-like pattern that extends across the observable universe. Mapping the cosmic web is a challenging but crucial endeavor for cosmologists. One of the primary methods involves analyzing the distribution of galaxies in large-scale surveys. By mapping the positions of millions of galaxies, astronomers can trace the underlying structure of the cosmic web. However, galaxies only represent a small fraction of the total matter in the universe. The majority is dark matter, which does not interact with light and is therefore invisible. To map the distribution of dark matter, scientists use techniques such as gravitational lensing, which measures the distortion of light from distant galaxies as it passes through the gravitational fields of intervening dark matter. This method allows astronomers to infer the distribution of dark matter and map the cosmic web more completely. Another technique involves studying the Lyman alpha forest, which is a series of absorption lines in the spectra of distant quasars caused by the absorption of light by hydrogen gas in the intergalactic medium. By analyzing these absorption lines, astronomers can map the distribution of gas in the cosmic web and trace its structure. The significance of the cosmic web in cosmology cannot be overstated. It provides crucial insights into the formation and evolution of the universe, the nature of dark matter and dark energy, and the processes that govern the distribution of matter on the largest scales. By studying the cosmic web, cosmologists can test their models of the universe and refine their understanding of the fundamental laws of physics. Furthermore, the cosmic web plays a crucial role in the evolution of galaxies. Galaxies form and evolve within the dense regions of the cosmic web, where they are constantly interacting with their environment. The flow of gas along the filaments of the cosmic web provides a continuous supply of fuel for star formation in galaxies. The cosmic web also influences the mergers and interactions of galaxies, shaping their morphologies and evolutionary paths. As we continue to explore and map the cosmic web, we gain a deeper understanding of our place in the universe. Now let's explore how the Black Widow pulsar's radiation affects its surroundings and what it teaches us about extreme cosmic environments. Shifting our gaze from the vast cosmic web to a single yet formidable entity, let's now turn our attention to the Black Widow pulsar and explore the profound effects its intense radiation has on its immediate cosmic neighborhood and the unique insights it provides into extreme astrophysical conditions. The Black Widow pulsar, a rapidly spinning neutron star, emits beams of electromagnetic radiation and high-energy particles with astonishing power. This radiation has a significant impact on its surroundings, particularly its companion star, which it slowly devours. The intense radiation emitted by the Black Widow pulsar bombards the surface of its companion star, heating it to extreme temperatures. This process causes the companion star to evaporate, gradually stripping away its mass. The material stripped from the companion star forms a swirling disk of gas around the pulsar, further complicating the dynamics of the system. This interaction between the pulsar and its companion creates a dynamic and ever-changing environment where matter is constantly being transferred and energy is being dissipated. Studying the Black Widow pulsar and its interactions with its surroundings allows astronomers to probe the behavior of matter under extreme conditions. The temperatures, densities, and magnetic fields in the vicinity of the pulsar are far beyond anything achievable in terrestrial laboratories. By observing the radiation emitted by the pulsar and its companion, scientists can gain insights into the fundamental physics of neutron stars, the properties of matter at extreme densities, and the processes that drive the evolution of binary star systems. Furthermore, the Black Widow pulsar serves as a valuable testbed for theories of particle acceleration and high-energy emission mechanisms. The pulsar's strong magnetic field and rapid rotation can accelerate particles to relativistic speeds, generating intense beams of radiation. Understanding how these particles are accelerated and how they interact with the surrounding environment is crucial for unraveling the mysteries of high-energy astrophysics. Looking ahead, our exploration continues as we uncover the great attractor's hidden secrets, examining the challenges of studying this gravitational anomaly and the latest theories about its nature. Switching gears to another cosmic enigma, let's now focus on the great attractor's hidden secrets, examining the challenges of studying this gravitational anomaly, along with the latest theories that attempt to explain this mysterious phenomenon. The Great Attractor, a gravitational anomaly located tens of millions of light-years away in the direction of the Centaurus constellation, presents formidable challenges to astronomers due to its obscured location behind the zone of avoidance, a region of the sky heavily obscured by the Milky Way's dust and gas. This obstruction makes it difficult to directly observe the Great Attractor and measure its properties, hindering efforts to understand its true nature and composition. Despite these challenges, astronomers have employed various techniques such as X-ray observations and indirect measurements of galaxy motions to probe the Great Attractor and map its gravitational influence. Several theories have been proposed to explain the Great Attractor's immense gravitational pull. One theory suggests that it is a supercluster of galaxies, a vast collection of galaxies bound together by gravity, which is responsible for the observed gravitational anomaly. However, the mass required to account for the Great Attractor's gravitational effects exceeds the observed mass of visible matter in the region, leading to the hypothesis that dark matter may play a significant role. Dark matter, an invisible and mysterious substance that makes up a significant portion of the universe's mass, could contribute to the Great Attractor's gravitational pull without being directly detectable. Another theory proposes that the Great Attractor is not a single, concentrated mass, but rather a region of space with a higher-than-average density of galaxies and dark matter, creating a broad gravitational gradient that affects the motion of galaxies over a large area. As we continue to unravel the cosmos's puzzles, our sights now turn to the gamma-ray emissions of the Fermi bubbles as we explore ongoing research into these structures and their potential connections to the Milky Way's supermassive black hole. Turning our gaze to another area of active research, we now consider the Fermi bubble's mysteries as we discuss ongoing research into these gamma-ray structures and their potential connection to the Milky Way's supermassive black hole. These massive, balloon-like structures, extending 25,000 light-years above and below the Milky Way's galactic plane, were discovered in 2010 by the Fermi Gamma-Ray Space Telescope. Their origin and nature remain a topic of intense investigation, with scientists exploring various possibilities related to the Milky Way's central supermassive black hole, known as Sagittarius A star. One prominent theory suggests that the Fermi bubbles are the result of past outbursts from Sagittarius A star. According to this scenario, the supermassive black hole may have undergone periods of intense activity in the past, during which it consumed large amounts of gas and dust, releasing vast amounts of energy in the form of jets and radiation. These energetic outflows could have inflated the hot gas that makes up the Fermi bubbles, pushing it outward into the galactic halo. Evidence supporting this theory includes the detection of high-energy particles and magnetic fields within the bubbles, which are consistent with the effects of past black hole activity. Another hypothesis proposes that the Fermi bubbles are driven by star formation processes within the Milky Way's central regions. According to this scenario, intense bursts of star formation could have generated powerful stellar winds and supernova explosions that collectively contributed to the formation and expansion of the bubbles. These stellar processes could have injected large amounts of energy and particles into the surrounding gas, creating the observed gamma-ray emissions. Distinguishing between these different scenarios requires further observations and modeling of the Fermi bubbles' properties, including their age, composition, and dynamics. Astronomers are using a variety of telescopes and techniques to study the bubbles in detail, hoping to uncover clues about their origin and evolution. As we probe deeper into the enigmas surrounding the gamma-ray emissions and the Fermi bubbles, we'll transition to an entirely different realm, focusing on the interstellar wanderer known as Oumuamua. As we journey to the end of our cosmic tour, let's reflect on the 25 strange cosmic objects we've encountered. From the Black Widow pulsar devouring its companion to the elusive Oumuamua hurtling through our solar system, each has presented unique mysteries that challenge our understanding of the universe. We've explored the Boomerang Nebula, the coldest known place, and the Diamond Planet, made largely of crystallized carbon, the Great Attractor, the Cannibal Galaxy, and the Red Rectangle Nebula each showcase the dramatic forces shaping galaxies. We also considered the Zombie Star, defying typical supernova fates, and Tabby's Star, with its perplexing dimming patterns. Hoag's Object and the Dark Flow revealed large-scale cosmic structures and movements that still elude complete explanation. The Methuselah Star, the Hypervelocity Stars, and El Gordo Galaxy Cluster each presented puzzles about cosmic ages, speeds, and the nature of dark matter. Ghostly neutrinos and blue stragglers added to the intrigue at both subatomic and stellar levels. The quasar tsunami and the magnetar demonstrated the immense energies at play in the cosmos, while the pillars of creation and the Fermi bubbles highlighted the dynamic processes of star formation and galactic activity. The hypothetical dark star, the Hercules Corona Borealis Great Wall, and the Thorn Zitkow object offered glimpses into theoretical possibilities that push the boundaries of astrophysics. Finally, the ringed exoplanet and the cosmic web illustrated the diversity and interconnectedness of planetary and galactic structures. Each of these objects, in its way, underscores a central theme. The universe is far stranger and more wonderful than we can readily imagine. They challenge us to push the boundaries of our knowledge and to constantly question our assumptions about how the cosmos works. As we continue to explore, driven by curiosity and aided by ever-advancing technology, what other cosmic enigmas await discovery? What are your thoughts on these cosmic mysteries? Which object fascinates you the most, and what other hidden wonders might the universe hold? Share your thoughts and theories in the comments below, and be sure to subscribe for more cosmic explorations. Hit the like button if you enjoyed this video, and ring the notification bell to stay updated on our continuing journey through the universe's endless wonders.